All right, class. So we're going to be going over the last section that we wanted to go over in class, but we couldn't. So it's going to be having to do with the chain rule. So my plan of attack is the first, let's say 1, 2, 3, 4. So I'm going to say the first 3 things that you're going to go over. It's going to take quite a bit of time to go through this stuff, but the first 3 kind of like slides, or like first 3 papers we're going to go through, are kind of like exploratory, and it's kind of like talking about the concept of what a chain rule will look like and what it is on a technical basis, and formally what it all means. And then the last one is probably what the last slide is probably what you're going to end up using the most for now on for the chain rule, and the majority of your homework problems are going to be. But nevertheless, you're still going to have homework problems on the first 3 slides, or the first 3 papers. Okay. So the first problem that you might see in your homework is something like this. The function of y is equal to 6x minus 10 can be rewritten as this: 2 times 3x minus 5. Okay. Y is also the composite function, if you look at it like this, of 2 times u. So if you look at this and this, it's saying like it's basically this is equivalent to this if u such that u is equal to 3x minus 5. So you want to write all this down, by the way. Okay, so you can take a minute to pause this and follow along with what I'm talking about. But you're going to have this and this are the same, such that u would be equivalent to this, 3x minus 5. How are the derivatives of this, this, and this, how are these all related? So let's take a look. Or I'm sorry, this too as well. So first, you want to take the derivative dy dx. So we're taking this guy now. We're just taking the derivative of y with respect to x. So what that's going to look like is just the derivative of 6x would just be 6, and then derivative of constant would be 0. So that'd just be 6. So that's okay. There we go. We got that. And then let's take a look at dy du. So if you have, so look at this one. Y is equal to 2 times u, and we know what u is equal to, but again, everything is in terms of u. So if we took the derivative with respect to u being our variable, it'd be what is the derivative of tu? So it'd be like, you don't have to write this, but what is the derivative of tu instead of x? It'd be tu. It'd just be 2. It'd be a constant. So you can pause that and think about that for a second. Okay. And then let's do one more. Let's do the derivative, finally, of this guy, of u. Let's do the derivative of u with respect to x. So u is the equation now, and x is going to be the variable. So du with respect to x. So what is the derivative of 3x minus 5? That'd be 3. How are these 3 related? Well, this 6 is equal to 2 times 3. So you can write as 6 is equal to 2 times 3. But each of these components, what it means is 6. Another way of saying 6 is equal to dy dx. dy over dx is equal to, and if you take a look here, 2 came from dy du, and then that's being multiplied to 3, which is du over dx. We came up with this statement here, and that's basically the idea of the chain rule. If you take a derivative of y with respect to x, but you include a weird substitution saying that, okay, 2 times, if we made this whole bold statement a u, okay, and you take it as y is equal to tu, or 2 times u, but knowing that u in itself is an equation that involves x, this is how it's all going to relate. The derivative of y with respect to x would be, take the derivative of y with respect to u, and you multiply that to the derivative of u with respect to dx. That looks really complicated, okay? But trust me on this, it's going to lead somewhere. That's the basis for the chain rule. So let's write this down. This is the basis, the basis for the chain rule. I want you to go ahead and try. So I'm going to write this down really quick. You try this one. Y is equal to 3 times, y is equal to sine of 3x plus 1. Let's set the inside here as our u, so u would be equal to 3x plus 1. Then using the same steps, I want you to find dy over dx, okay, sort of like in the same way we did up here, okay? So why don't you pause this, and then when you unpause it, I will show you the answer. I'm not really going to go into too much detail about it. Okay, so go ahead and pause it and try it, and when you're ready, unpause to see the answer. Let me go to the answer now. So it's written in green, okay, so it's the same problem. So let's, dy is equal to the derivative of dy, so the derivative of y, so it's literally the derivative of y, which is sine of u with respect to u though, so this is equal to u, 3x minus 1, or 3x plus 1, okay? Take the derivative of this with respect to u. If you take the derivative of sine of u, or sine of whatever's in there, it's going to be cosine of u, okay? Du dx, so if I took just the derivative of u with respect to x, it'd be d times d of dx, the derivative with respect to x of 3x minus 1, or 3x plus 1, that'd just be 3. Let's make a relationship really quick. This is basically dy over du is equal to dy over dx, which we got, I'm sorry, dy over du, dy over du, which is, so it'd be like this, dy over dx. Basically what this is saying is dy over du is basically cosine of 3x plus 1. So everything has to be in terms of 1. So I substitute in 3x plus 1 back into that, back into where u was. I multiply it to dy over dx, or du over dx, du with respect to x. As that is equal to 3. So that's pretty complicated, but take a minute to kind of just study over that. Okay, and I'm going to move on to the next slide. Okay, so I do apologize. The first few slides is really hard to understand the concept of, but then towards the end, it's going to get really easy for what you're supposed to do. Okay, so this we're going to further explore what just happened. Okay, so you could look at functions as sort of a composition or composite of maybe two functions that are actually differentiable, okay, but like they're directly integrated within themselves, okay, they're like directly like linked within each other. So the derivative, so let's take a look at a composite function. It'd be the f of g of x. The derivative of this composite function, if you were to take the derivative, you would have to take the derivative of f of g of x first, then you multiply through the derivative of the inside, which is g of x. Okay, so write that down. And then probably what you're going to see more is this. This is what's called Leibniz notation. So this is one way of approaching the same thing. The math's going to come out the same, but the notation might look a little bit different. Okay, and this takes a long time to get used to in calculus. Okay, let's look at, if you had an equation y is equal to f of u, let's say that it's a function of something of u, and then u itself is also differentiable. It's a differentiable function, so it's another function that you can differentiate. So it's y is f of u, and then guess what? Whatever u is also a function in itself. What we found out earlier was dy over dx. If you took the derivative of y with respect to x, though, like the most common component and most common variable between u and y, okay, then it would be dy of du times du over dx. Another way of looking at it that I don't like is you can look at it as the derivative of f with respect to g times the derivative of g with respect to x. So we're not going to go too far into that. I like sticking kind of like up here, okay? So that being said, let's try a problem. Let's see where we are right now. Okay. Let's try a problem. So right now you have f of x looks like a composition of two functions, cosine of something, and then within that something is another function you could take the derivative of. I could take the derivative of cosine if you think about it. That's just sine of x, or sine of whatever's in here. But then at the same time, you have another thing within here that's also differentiable. So I'm going to show you like the textbook classic way of doing this. And then by the last slide, which I'm actually approaching very quickly, is the way that you're probably going to most likely do it on your homework or just in the future. But I have to show you the textbook clean way of doing this. In fact, this is the way that I typically use now. Give me 1 second. Okay. So first, let's define that u. Remember, we have to define a u. So I'm going to say that this inside function, this guy here, is in itself differentiable. Okay. So we can rewrite this as f of u is equal to cosine of u. Okay. So maybe make that our first step. Okay. And then we know that u is equal to pi half minus 3x. And then let's just take first the derivative of f with respect to u. That's pretty simple. Cosine of u would just be, what is it, negative sine, I think, of negative sine of u, right? And let's take the derivative of u, because I know I can take the derivative of that guy. That's du. Du would just be 0. The derivative of a constant, pi over 2 is a constant, it's not a variable. Is just 0, and then the derivative of minus 3x is just minus 3, and then we remember, or that we know, that the df of dx is the composition of, you have to take the derivative of df du, you have to multiply that to the derivative of u dx. And then what you're going to do is you're going to combine these two. So it's negative sine of u. And since our final answer has to be in terms of x, let's plug back in what u was. U is equal to pi over 2 minus 3x. So that's pi over 2 minus 3x. Everything has to be in terms of x. That's what this is saying. The df of dx is equal to this times this, okay, negative 3. This can't have an actual u present. It actually has to be in terms of x, okay? It's because our final answer has to be in terms of x. So our final answer would be negative 3 sine of pi over 2 minus 3x. Okay? That's it. That's our final answer. Oh, actually, I think I did it wrong. I think it's minus sine times minus 3. That's positive. Okay, so that's our final answer, right? And another way of kind of approaching it too, so this is alternative, this is the alternative way, was you could have set it up like this. Let's see, df dx, you knew firsthand was already df with respect to u times du over dx. And then you could have just said that the derivative with respect to x of, what is f? Well, f is equal to cosine of u, or cosine of, remember, it has to be in terms of x, so you can't leave it in u. You have to substitute back in what u was equal to, because the actual u equation has x in it, so that's why we want everything in terms of x. So it's cosine of pi over 2 minus 3x times the derivative with respect to x again of u. So it's pi over 2 minus 3x. Pi over 2 minus 3x. So this is u, and then this is f, okay? So get it, the derivative of this guy, that's the derivative of f, that's df of du, but it has to be in terms of x this time, times the derivative of u with respect to x, which is pi over 2 minus 3x. I think this one's a little bit more confusing, so I don't really quite like this one as much, doing it this alternative way. So the derivative of this whole thing is negative sine of pi over 2 minus 3x times negative 3 is equal to positive 3 sine of pi over 2 minus 3x. Okay, so let's try to relate back to our original slide here, or one of our original slides. I think this is a really good example. This has a component, the cosine of this guy was sort of like this. The composite function, if you remember back to one of your original slides, it's the composite function of f of g times x. The derivative, that would be the f of g of x. So if you think about it, it'd be like this is the f cosine of another function that you can take the derivative of g of x. So this was literally the f prime of g of x, f prime of g of x, and g of x is right there, and then you have to take the derivative of g of x. See? The f prime of g of x times the actual g prime of x, meaning the derivative of the inside guy, okay? So this one's really tough, okay, to understand. Let's see, that's all conceptual and that's all formal, the way that you're supposed to learn it with all the notation, the proper notation. Here's what it's going to look like in practice, okay? So we're finally at the last slide. So let's take a look at an example here. This is called the outside-inside quick method. This is when you can really identify two things that are you're taking the derivative of. Okay, so let's take a look at an example. Okay, so I noticed two things. There's an overwhelming big, so this one's really tricky to see, but I see this whole thing to the power of -2 is in itself what we call the outside function. I have to take the derivative of this, meaning I have to pull down this power, -2 in the front, and then I have to subtract 1 from here, okay? That's the outside function. However, you can also take the individual derivatives of the inside guy. You have to be able to define and see two different functions that you could take the derivative of. So this one is not quite as, I mean, it could be easier to save you time, but the last one, the reason why I liked it is because as long as you knew this fact here, df of dx is equal to df times du of x, and then you define what your u is, and then you start taking derivatives of both the components, like the bigger function on the outside, and on the inside you take the function here, then I don't know, it just works out a little bit easier if you start defining things with notation. This one, you skip all those steps, and you have to be able to define, like, this was essentially what my u would be. So this is what they call the inside function and the outside. Outside inside means you take the derivative of the outside times, this is not formal, this is just a derivative of the inside. This is a really quick, fast process that you might need a master. You need a master for the AP exam, or just in the future if you're doing faster level math. But again, nothing beats having all the notation written out, because this can lead to a lot of errors, and it's really hard for teachers or fellow students or like fellow workers, co-workers, to follow what your math is, you know, if you're trying to work all this stuff out. So with notation, everyone can follow along. Without notation, this is really informal. It's going to be a lot harder to follow along. Okay, so let me show you what I mean. So the outside function is, I notice that this whatever's in here, okay, could be just like a blob. If it's to the power of -2 and it's a variable inside, I'm going to take down the exponent in the front. So it'd be -2 times x plus, and we don't touch the inside. The inside stays stagnant, but then you just work with the power rule out here, okay? And then you have to take the derivative of the inside. That you take the derivative of the inside, which is 1 plus, and then if you think about this, this is another way of looking at this, is x to the power of 1/2. So you would drag out the 1/2 out in the front, and you subtract 1 from here, which is -1/2. That would be the answer. That's it. So it would be -2 times x plus root x third, and then if you want, you don't have to color code like I am, but it makes it a little bit easier. But I know this is 1/2, and I know that x to the negative 1/2 would be like same thing as 1 over root x. Okay. We're getting a little bit too far, but I think I was okay with this here. Okay. Let's try this one. You can try this one on your own. This is another example. This one is, why don't you find the derivative for sine of x squared plus x. So let's define the outside function. I notice it's the sine of something within here that is differentiable. So I could take the derivative of the outside. It's the sine of whatever is in there. Okay, that's the outside. And the inside is another little kind of mini little function, the inside function that you can take the derivative of. So again, following the rules, it's the derivative of the outside times the derivative of the inside. What's hard is you have to define all this stuff. So the derivative of the outside is cosine of whatever was in there. Okay, in this case it was x squared plus x, which you don't touch. Okay, now you take the derivative of the inside, which is 2x plus 1. And that's it. That's your final answer right there. Okay. So you have two options basically when you're doing this. You have the outside inside function, which you have to be able to really see the outside and the inside. It's the same thing as what we did here. So with the notation, so this is the one with the notation. This is more formal. F of x is equal to cosine of whatever's in here. I know whatever's in there. Again, it's sort of like an inside function. That's a u, right? And then you have to find the df of dx. We know that df of dx is equal to the derivative of f with respect to u times derivative of u with respect to x. Maybe the outside-inside function looks a lot like this now. Now with the outside-inside function, hopefully this explains it a little bit better. Define f of u as cosine of u. U is also equal to that. So df of du in terms of u would be you just take the derivative of f with respect to u. That's this right here. That's f of u. That's f of u. Let's find the derivative of that with respect to u. That's negative sine of u. Du with respect to x, that's the inside function basically. So this is the outside function. This is the inside function. U is equal to 1/2 or pi half minus 3x. That's a constant. 0 minus 3x. That's going to be 3. So that's going to be minus 3. And then you just combine them. The derivative of f is going to be these two components. Multiply the derivative of the outside function, the derivative of the inside function, or df with respect to u times du with respect to x. Okay. And then you, but remember, everything has to be in terms of x, though. I'm still asking for everything in terms of x. So you make this negative sign of u, you substitute back in what u is actually equal to. And then you multiply it to du dx, and then you should get this. So they're actually the same exact method, but one is a little bit more wordy and a little bit more, what is it? Has a lot more notation. But in your book, when they communicate these things to you, this is how they're going to communicate it. If they communicate it with the inside function, it's not so certain that everybody understands the same language. Well, because they're in the book, they're not going to tell you they're not going to write out outside and inside for you. They just sometimes just do it. But if they write it out like this, it's a little bit easier to follow along. It's their way of basically saying, this is the derivative of the outside function, df of du. This is the derivative of the inside function. I define my inside function as u. This was my inside function. I defined it as u. Okay, so it's basically saying the same thing. This is just, this paper is the formal way of doing it. This is the informal way that you might be doing on your homework or in your future exams, on my exam or even the AP exam or just on the job as well. Okay. All right, guys, you guys take care and you guys have a great day. Bye.